See my slides?
Perfect. Yeah.
Nice. All right. So, well, hello, everyone. I am Stefano, and I'm going to present this work on Neuro-Symbolic Constraint programming for structure prediction that I've done together with Paolo Dragone and Andrea Passerini at the University of Trento. So first of all, what is this work about? So we are interested in structure prediction tasks where the output is subject to arbitrary constraints and the input can be composed of complex sub-symbolic items. So let me unpack that. So to do that, let me start from an example. Here, what you see on screen is a bunch of black and white sub-symbolic images, right, of digits that represent a handwritten equation. And in particular, the equation 41 plus 411 equal 452. There you go. This equation is syntactically correct and semantically correct as well. The sum actually matches. So the idea is that in order to perform this kind of prediction, so starting from the images, getting the equations out of that, that's a highly non-trivial task. It involves combining a bunch of different techniques. And in particular, what we do in order to achieve this, to perform this kind of task, we have to combine structured output learning, which is now classical technique used for predicting structured outputs from inputs, for instance, parse trees from text, together with constraint programming, which is a class of techniques for imposing constraints on structured objects, as well as neuro-symbolic integration, which enables us to compute predictions from sub-symbolic inputs, in this case, images. So we take these three elements, we put them together. I will show you in the next few slides how. So first of all, let me start from the basics of structured output prediction. Here, the idea is since computing a mapping between inputs and outputs that are both structured is quite complicated, what people do typically is that they define an energy function that, given an input, scores all potential outputs based on their energy level. And the lower the energy level, the higher the compatibility between the given input X and the corresponding output. Now, what we want is essentially to learn an energy surface that has low energy for all the correct outputs and higher energy for all the bad outputs. Doing so revolves techniques for doing so revolve around standard strategies from machine learning. One, something that really pops out in this setting is that learning requires to perform inference, which can be quite computationally challenging, let's say. And I will show you in a second how, why. Learning at an intuitive level works more or less like this. So here on the left image, you see an energy surface where the correct output yi has a higher energy than a worse output yi bar. So intuitively, what you want to do in this situation is to push down the energy for yi and increase the energy for the bad output, so that you achieve something along the lines of the image on the right. Typically, this is achieved by running an interactive procedure in which you iteratively select examples, decrease the energy of the correct output, and increase the energy of the worst offending output. So, for instance, the output that has that is wrong, but has also the lowest element, lowest energy among all the wrong outputs. Once you have a model like this that assigns low energy to high quality outputs, in order to obtain a prediction for a new input, what you do is you solve an constraint optimization problem of the kind shown on screen here. So the idea is that in this case, we are maximizing the opposite of the energy. It's called a score, but it's exactly the same thing with a minus in front. So in order to obtain a prediction for some input X, we maximize the score, aka minimize the energy of the corresponding output. And where here the two novelties are that on the one hand, we have a machine learning model that models the energy function, in this case just a simple linear model where the weights W are learned and the features phi associate some representations to the pair XY, to the input-output pair, and are given in this particular case. And the argmax runs over only feasible outputs, and the feasible outputs are defined by constraints that the user has given. For instance, in the case of equations, that the sum is actually correct. Now, how do you solve this in practice? Well, it has been shown that in order to solve inference for this kind of models, it is often enough. Well, it is actually very convenient to encode the optimization problem as a, a constraint optimization problem, so a mathematical optimization problem. And in this case of a handwritten equation recognition, it will look something like this. So just maximize the score of the output, find the highest scoring output in the space of all formulas, of all sets of three numbers that are all three positives and that whose sum actually matches, and so on and so forth. These are the hard constraints in the problem. In practice, this is often implemented using languages like NeSy, and this is exactly what we do. So NeSy is a generic, rather general, high-quality language for defining constraint satisfaction and optimization problems, and it can be used to encode the kind of inference problems that we had on screen. This is exactly the code that we use to solve the equation recognition problem in the paper, and that I've shown earlier. All right, so far so good. I have shown the basics, the kind of the work that we build on. What do we do in addition to this in this paper? Well, we make all of this deep, in the sense that we take structured output prediction under constraints, and instead of using we plug it as a layer on top of regular neural networks to refine their predictions. So here, the new pipeline looks like this. First, we use a neural network. Here it is called G, right here, that takes an input, for instance, an image, and outputs a digit in our case, right? This prediction is made in without knowledge of the constraints themselves. Now, we have an additional layer on top that works according to the principle that I just described, and that just, refines the output of the neural network so that it is more compatible with the constraints themselves. So, and this is done again by solving an inference-like problem, where here you see there are three terms. On the left, we are maximizing the, we are looking for the complete output y, so the equation y, let's say, that has maximum score, just like in the original structured output prediction problem, and this is the first term. And the two additional terms also guarantee or encourage the output to be compatible with the output of the neural network. And this is the second term. So the two, for instance, should look like according to some weights that have been learned. And there is also a distance function that enables, for instance, one to say, okay, look, the output should be at least this different from the input. Okay. So again, the idea is we take a raw input given by neural network and refine it to make it more compatible with given constraints using structured output prediction. All right, as an illustration, this is exactly the architecture that we use for equation recognition. On the left, you see some input images. In the black box, you see that we use a convolutional neural network on each input image independently to output a corresponding digit. And there are some mistakes in the recognition which actually make both the output both syntactically and semantically wrong. And then we apply our new layer to obtain an improved output that is compatible with the constraints. And you see that on the right. Okay, now we have this new layer. How do you train this beast? So the idea is very simple. We just use techniques from structured output predictions, which come very handy here. We define a loss. This is just the structure hinge loss, and it basically penalizes the model for being too complex and for associating the wrong energy level or score to the right outputs. And in particular, it penalizes model that assigns higher energy to the wrong outputs, essentially, or lower scores to the right outputs. And again, this is done in the spirit of, this is optimized in the spirit of structured output prediction by iteratively picking outputs that have the wrong energy level, so that they have too low on energy, even though they are wrong, and then computing the gradient of the loss with respect to these examples. And this automatically gives us a way of computing weight updates through the network through the chain rule, essentially. So this is all straightforward. Now, does it work? Well, we have checked whether this is actually the case by comparing our approach, so a neural network with a constraint layer on top, against 3 different alternatives. One is just a simple CNN that is applied independently to all images. One is a CNN that is followed by an LSTM layer that tries to smooth out the prediction across the sequence of digits. And finally, the original method by construct that has a similar architecture but does not use a neural network. And the results, this plot shows the test loss over as training size increases for the four alternatives, and this shows that our approach is clearly below the red line, is clearly performing much better than the others. And this is due specifically to the fact that our approach manages to improve the both the performance of the overall network, both in terms of semantic and syntactic error. The other approaches, then, well, they perform less well, and in particular, the CNN plus LSTM combined pipeline does not perform as well as our method, despite the fact that there is actually, it should take into consideration the dependency across digits. Another point that we made in this paper is that deep neural networks tend to not address semantic errors, meaning that even the LSTM, which is the more complex architecture that we use here, tends to perform really well when it comes to syntactic mistakes, like realizing that the plus symbol must come before the equality symbol in the equation, but they perform very poorly in terms of semantic mistakes, so basically that the sum should be correct. And this is what you see. You see a CNN on the left and CNN plus LSTM to the right. They both perform quite poorly, especially in terms of semantic mistakes. All right. So this is basically it. So just to clarify kind of the relationship between this work and other existing alternatives, here we basically have a structured prediction layer on top of a neural network. This is related to a number of different competitors like BigProblog, NTP, and so on and so forth. However, our approach is designed specifically to handle hard constraints. So the output is guaranteed to satisfy them, and also it is designed to handle generic constraints, for instance, numerical constraints that most other approaches do not work with. It also has some limitations so for instance, it does not really deal with probabilities, although it could be adjusted a little bit to work with that. And it only focuses on maximum posteriori inference. And yeah, I suppose as for limitations, learning inference can be quite expensive because we would have to run mini-zinc every single time. This is reasonable for our task, but it could take way longer on more complex tasks. And we are looking into approximate inference to solve this. Does not, as I said, it does not really deal with probabilities or with marginalization at all. I guess this is about it. So yeah, thank you. Do you have any questions?